So I have a can, a cylinder with an open top. I know the volume of the can, so whatever I'm doing, it's not trying to maximize or minimize the volume of the can. Let's see. Here's the magic word, minimize. We're trying to minimize the cost of the can. And we have the cost for the sides and the cost for the bottom. There is no top. It's an open can. So let's see. Can, cylinder, circle, and there we go. There's my can. The bottom of the can is a circle. The area of a circle is pi times the square of the radius. But that's not the question. The question is the cost. But I know the cost is the bottom, 15 cents per square centimeter, so 15 cents per unit area. So I can say the cost for the bottom of the can is 15 cents times the area. Then we have the lateral surface of the can. Well, the lateral surface of a cylinder is really just a rectangle that we then bend around the circle. So the length of that rectangle is the circumference of the circle, the circumference of the can, which is 2 times pi times the radius, times the height of the rectangle. Well, the height of the rectangle is the height of the can. So distance around the circle times height of the can. But that's a problem because we're only allowed to have one variable, and now I have two. I have 2 pi r times h. So I'd like to write one variable in terms of the other, and really I'd like to write the height using the radius since I already have r in the other part of my equation here. Fortunately, we have another piece of information, and that is the volume of the can. The volume of a cylinder is pi r squared times the height, and I know what the volume is. It's 24 pi. I would like to solve that for h, so I'm going to divide by pi both sides. Oh, those are gone. That's good. And I get h is 24 over r squared. So now I can use that in place of h up here. This is 2 pi r times 24 over r squared, which is, let's see, we don't need all those r's, 48 pi over r. So there's the area of the lateral surface of the can. But again, I'm not trying to do anything to the area. I'm trying to minimize cost. Well, I know the cost of the lateral surface material is 5 cents per square centimeter. So I'm going to do 5 cents times that. .05 times 48 is 2.4. So I think I have all the pieces now, and we can put this together and come up with a function for the cost, which after all is what we're trying to minimize. So the cost is the cost of the bottom plus the cost of the lateral surface. And there's what I want to minimize. Now it's time for calculus. I'm going to take a derivative. 2 times 0.15 is 0.3. And this is r to the negative 1, so minus 2.4 pi over r squared. And I want to know, where is that 0? So a little equation to solve. I got 3 pi r equals 2.4 pi over r squared. I'm going to divide by pi. I'm going to multiply by r squared and divide by 3. And I get r cubed equals 8, because 2.4 divided by 3. Oh, sorry, 2.4 divided by 0.3. I was going to say 2.4 divided by 3 is not 8. It isn't. But 2.4 divided by 0.3 is 8. So I get a radius of 2. Let's see, the question was, find the dimensions of the can. So I got r. If I know r, I can find h. H is 24 over r squared, which is 6. And we have the dimensions of the can. Just to check and make sure we've found a minimum cost rather than, say, a maximum cost, which would be, bad. Let's take another derivative. So I got 0.3 pi, and then this is r to the negative 2, so I got plus 4.8 pi over r cubed. When r is positive, 4.8 pi over r cubed is positive, and if I add something positive onto that, I end up with something that's positive. If the second derivative is positive, then I have found a minimum. I have something that's concave up, and I found a minimum.